Hello students, welcome to my another video, and today's topic will be on the SoC architecture, that is unit 2. So in the earlier lecture I have covered the basic architecture of the initiator, the basic bus, the multiple initiator and the bridge bus. So I hope you have understood the topic and the basics of the SoC environment, how it is going to work and how it is being processed into the real world. So now we'll be discussing about ARM AXI bus architecture. Okay, so it is the most crucial one, and it is the complex IP of all which the ARM has provided, and we'll try to understand the functionality of this, by which we just understand how many types of signals are there and what are the current favorites of it, and supporting out of order operations using tags, what is network on chip, what is simple ring, what is network on chip, switch fabrics, and there are something more about it. So I have actually downloaded this specification file from the ARM. So this is the specification file which you can download from the ARM website for the AXI. So this is, we'll be discussing about the basic architecture, how many signals are there. So basically the signals which are involved, there are 5 independent channels. First is write request, then second is write data, then we have write response, then we have read request, then we have read data. Okay, so these are the 5 major channels which are being involved in development of AXI architecture. So let us just have a look at the diagram, how it is managing the interface. So the basic architecture, the basic idea is that there is a write response and write request signal which is being initiated by the slave and the master. Okay, so this is a master interface and this is a slave interface, subordinate we can say. And when the slave is ready to accept the transaction, so this write response will going to be high, and the write request signal the slave will be giving to the master, okay, that it is ready to accept the data and you can initiate the transfer. So these are the two major signal which you have to keep in mind for understanding the architecture. So this is the write request which is named by using AW, and this is second signal which is write response which is being mentioned by B. Okay, and there is a write data. So write data is like represented with W. So whenever the write request channel is high, so the write data channel will going to write the data into the memory of the interface. Okay, then there is a read request, okay, and there is a read data as well. So in my previous session I have discussed that I'll be discussing about some of the that clock pulse, how we are going to check the clock pulse and how the functionality of clock pulse is being used. So we'll just try to have a look by using a Verilog code, and just have the observation how clock is working and how we are doing it. So there is, I'm using a EDA playground. So we'll try to write a code for managing the clock. Okay, so this is module test bench and then end module. Then we have reg clock. We are declaring clock as 0, and always block is there. Always block, by which we can create a clock begin and end. and that's how I'm going to trigger the clock. Okay, so for observing the clock in the waveform, I need to dump the file as well in the to see the RTL and the wave schematic. So this is the basic diagram which is being involved. Okay, and there is some more keywords which we have to write to dump the file. So I'm creating that dump.vcd. VCD is the file extension which we are using. If you want to know more about the Verilog, how you have to code it, so you can go to VLSI Insights. Over there is a channel, so you can just learn how to code. There is every material available on that page. So now I'll be using this LDEC software. So if I run this code, so let us see, the waveform will be created, and okay, so I hope this is visible to you all. Okay, so I'm zooming it for you because so to make it more comfortable. So let us just observe the pattern how the clock is generating. Okay, so there are two things. One is like, okay, so in digital systems there are two things which we have to learn, that is edge and one is level. So we know this thing, edge is this point. Okay, this is the edge point. I'm changing the color of this. Okay, so this point is known as edge. Okay, this is the edge. If the clock is rising from 0 to 1, okay, if the clock is rising from 0 to 1, so we can call it pause edge. Okay, if the clock is falling from 1 to 0, so it is the neg edge. Why I am explaining you? Because I'll be using this terms while explaining the XI protocol. So it will make things easy to understand what you have to do and what are the parameters associated with it. So there are certain things, okay, apart from that. So if I discuss what is level, so this is level, this whole point which I have highlighted over here, so these are known as level. Okay, so this is level 1, I can say this is level 1, and when the level is at the 0 point low, so this is level low. We know that latches work on the level and the flip-flop works on the edges of the of this clock. So this is the standard clock which we are taking as in sample. Whenever there is a pauses of the clock, the output, the results will going to map on each of the pauses of the clock. And if we are willing to have the output on the neg edge of the clock, so this will be the neg edge. Okay, these all the points will be the neg edge. This point, okay, so this point, the points which are being highlighted with the red marks are the negative edge of the clock. Okay, so whenever we are writing the code, like we want something to observe, like we are expecting that some code should run in the positive edge, we should get the sample in the positive edge, so we'll be using pauses and negatives. So to make it more clear, I'll try to make you understand using a code. Okay, so I'm making a simple code of adding a logic. So some of you might be aware of the Verilog syntax, and some of you might not be aware. So that's a very basic syntax which we are going to use. Okay, so first I have to use clock, and then again I have an input. I'll be giving a range to it so that we can just have a close look what are the parameters indicating us in the output. So for the output, we have to declare the output name as an output, and then again we have to give the range for it. Then my output will be this out. Okay, so this is all about this module, and then we have to end the module. So this is the basic syntax of the Verilog code, and then I'll be using a assign statement. to get the output of each and everything. Okay, so because like we want that our sample, our output should be on the positives of the clock and the negatives of the clock. So what I'm expecting that I should write a always statement in a control statement. Okay, that will be a control statement, always at the rate, that means positives of the clock, positives of the clock. Okay, so I'll write this out is equals to A plus B. So whenever I'm like whatever, whenever I'm putting the input A and B, so my output will always going to reflect at the positives of the cycle. Whether I put inputs at the negative point also, then also I'll be able to calculate, I'll be able, like I'm getting the output at the positives of the clock only. So I'll just write the initial conditions for that. So reg, okay, so I have to decide the range as well, again A comma B, and then wire is used for the output. So that is again A 7 down to 0, we are using out. Then to connect it, we are using a simple syntax. Okay, so to connect the environment, this test bench environment with this module file. So I'll be giving A is equals to 1 and B is equals to 2. Okay, so what I'm expecting, I'm giving this conditions at the 0 time because I have not provided any type of a delay. So it will be working at the 0 time only, but my output will going to show at the positives of the clock. So we know this thing, A, like A and B will sum up to and give us to 3. So 1 plus 2 will going to give us 3, but we have to observe that when it is going to give us the result 3. So to check this, I'm again running this tool. Okay, so there is a problem over here. Okay, so there is a syntax error. We'll just try to fix it and we are done with it. Okay. Okay, so output, okay, we have to declare output as in reg level. So this is how the code is working, and we are able to see the errors over there in the file only. So now you just have a look at this. Okay, so I'm deleting the unnecessary signal right now, so to make a clarity. So you just see that I have given this A and B at the 0 time. You can see this time strain. Okay, I'm trying to zoom it for you all. So you can see that I have given A and B values. Okay, A and B value as the 0 time, and at 5 nanosecond. Okay, I'm at the 5 nanosecond, or we can say at the positives of the cycle, I'm getting the 3 input. Okay, so this is the basic fundamental which I wanted to teach you using this, like how we are going to sample the output. So I'm taking one more scenario. If suppose I put like I gave the like inputs A and B at the 6 nanosecond. Okay, so then what will be the condition for that? Okay, so I just gave the delay for 6 nanosecond. So now my clock cycle was on 5, like 5 it was on pauses, then negative it is coming at the 10 nanosecond. So if I'm crossing the point, okay, if I'm crossing the edge point, so we'll just try to figure it out at what time, at what cycle the output will going to reflect. So you see this thing, it is very clearly visible that actually I have missed this time strain of 5. So I have put my input signal at the 6 nanosecond. So the values which I'm getting or at the output is getting at the next positive of the cycle, right? So this is the next positive cycle which I'm showing over here. So you can see like the results are coming at the that is 5, 10 and 15 nanosecond. Okay, this is the 15 nanosecond I'm getting, although I'm giving my input at the same 6 nanosecond, but my output is coming at 15 nanosecond. So this comes to be an sequential circuit. So if I try to make a combinational circuit, so there is a simple change in this. So combinational circuit, we know that as soon as the input we are going to assign, okay, that at the same time the output will going to reflect. So let us just check the waveform. So how it is going to happen. So you see that, okay, I'll just remove this unnecessary signals again. So look, I have given this time strain for 1 and 2, okay, at the 0 nanosecond, and then you can use this output signal, okay. Okay, so you see that 3 is coming at the same time. Okay, now I'll just take one more corner case. Okay, so earlier I took a delay for 6 nanosecond and it was coming on the 15 nanosecond. So now it will be clear to you all that the output will be coming on the same time strain, whatever the delay I have provided in that. So you see that I have given the input at 6 nanosecond, okay, and at the same time I am getting the output. But earlier when I was sampling with the pausage of the clock, so the output was coming on the next pausage of the cycle. So I hope this point is quite clear to you all, what is clock and how we are going to sample the output data. So let us just roll back to the AXI protocol. So we are having this write request channel, write data channel, and write response channel. So what response channel, what address and control will going to do? It will going to take have necessary input signal. It will going to have address, and it will going to have control signals, whether the transition is being written or not. When the transition is being completed, so there is a response which the subordinate interface used to send, that the transition is complete, so it will going to response, okay, that the data is being completed and it has been received. Then again we are having the similar structure for the read mechanism. So when we have written the whole condition, okay, so there is a another method by which we can just read the outputs, okay. We can just have a clear look at the output, what we have written in that, and just by using the read request channel. So whenever the read request channel will be high, at that moment we won't be able to write the uh, conditions, we will be able to write the data. Only what we can do, we can just read the data what the master has written on the subordinates, okay. So these are the basic things which you have to keep in mind. So these are the only 5 major signals which are associated with the AXI architecture. I'll just repeat it again: write request, write data, write response, read request, and read data. So these are the 5 basic channels. Okay, so moving forward with the okay, so I discussed something regarding this address and control channels. So what are address and control channels will be indicating to? So channels definition, basically write and read request. So whenever the valid and ready will be high, so we call this is a two-way two-way handshaking mechanism. Handshaking mechanism is a fundamental in which we are acknowledging our master slave, okay, the valid condition is high, the master is ready to send the transaction, then it can have a it can readily adapt to the transactions. Then we have this last signal. So last signal is indicating that when the data is being successfully completed and being finished, so the last signal will go into high, and it will also indicate that this is the last data which it is being transferred from master to the slave. So it will going to indicate, okay, this is the last transfer and no other further data will be coming, okay. So this includes the last signal which indicates the transfer of the final data item of the transaction. Then we have a data write channel, and then we have this write channel which is used to manage the subordinates, okay. So the data signal which can be like 8, 16, 32, 64, 128, 256, 512, 1024. So this IP can hold 1024 bytes of data with a property, okay. And the byte lane for every 8 bits indicating the byte of the data are completely valid. So this is all about the write data channel. So write data channel will be having a range. The range start from 8 bits, 16 bit, 32, 64, 128, 256, 512, and 1024. Then we have a write response channel. Write response channel is responsible for giving the response in the output, that the transition, whenever we are writing the response channel to respond with write transition, requires completion of signal onto the wire response. So basically it will going to response whether the transition is being written or not, or whether the master slave is ready or not. So this is the basic signal which has been acquired in the AXI IP. Then we have the last signal, okay, that is the read data channel. So read data channel, again, read data channel will be having the same width. It will be having from 8 bits to 1024 bits, and the width is indicated using data width property, and the read signal is indicating to the completion of the status of the read transition. So these are the 5 major signal which you have to keep in mind, and I hope this is fundamentals are being understood. So there is like little bit point of confusion happens with the student that what is 8 and 16. So 8, 16, 32 are the data size which it can hold, and it can hold up to 1024 byte size of the data. Okay, so what is the typical topologies that it can have a shared request and a data channel, shared request channel and multiple data channel, multi-layer. It can also support register slices. Okay, so as we have discussed that we'll be discussing about the out of order supporting header. So it will be a another corner case of this AXI support topology.